Hey guys, welcome to the notes for section 6.5. Today we are going to talk about solving a system of equations by the substitution method. You did this a little bit last night. You solved equations by the equal values method, which is very similar to the substitution method. And today we're officially going to go over how to do the substitution method when you are solving a system of linear equations. So up top here, I have simply given you a box with all the directions. I don't really need to read through the box. At least I'm not going to do the whole thing. I will come back and refer to this box as I do the first example. Okay? So the one thing you should know is when is the best time to use the substitution method? Because eventually at the end of this chapter, we want to be able to decide what method to use depending on what the problem looks like. And I think the best time to use the substitution method is when one of the equations can easily be solved for one of its variables. Or at least, frankly, I think it's when one of the equations already has a variable by itself. Like if I had y equals 2x plus 3 and 3x plus 2y equals 10, this would be a good substitution problem because the variable is by itself. But even if you just had an equation like 2x plus y equals 3, where it's easy to get the variable by itself because it doesn't have a coefficient, or it has a coefficient of 1, that's a good time also. All right, so that's when you use the substitution method, primarily when a variable is already by itself, I think. And here's how you use it. Your first job is to solve one of the equations for one of its variables. All right? Get a variable by itself. Again, this method is best if a variable is already by itself. And this is the big step right here. Substitute that amount into the other equation in place of the variable. So let's see how that's done. All right, so I have an example here, and of course, in my example, a variable is not by itself already, but it looks pretty easy to me to get this y by itself, because that y does not have a coefficient. And I would get that y by itself by adding 2x to both sides, and I would get y equals negative 3 plus 2x. And now I have a variable by itself, and here comes the key to the substitution method. Take what y equals and substitute it in for y in the other equation. So I'm actually going to rewrite the other equation, but I'm going to replace the y with what y equals. And it might look like this. Instead of 3 times y, it would be 3 times negative 3 plus 2x plus 4x equals 14. All I did was rewrite this problem, but I replaced the y with what y is equal to. That's why it's called the substitution method. And now you have an equation with only one variable, and you can go ahead and solve it. So I would distribute the 3, negative 9 plus 6x plus 4x equals 14. I'd combine my like terms. Negative 9 plus 10x equals 14. This is going to be yucky, isn't it? I would add 9 to both sides. Hope this is right. 10x equals 23. And I would, just looking to see if I've done everything right, I guess I would divide by 10. And x equals 23 tenths, or 2.3. Man, I wonder why I gave you a problem that didn't have a nice answer to start out. All right, and then I would take that. I now have half of my answer, and I would substitute that back in up here. And I would say y equals negative 3 plus 2 times 2.3. That would be negative 3 plus 4.6. And And negative 3 plus 4.6 is 1.6. And so my answer is 2.3, 1.6. That is apparently the ordered pair, which makes both of these true. It makes me a little nervous. I'm going to think about that. Let's see. I could check to see if it's right. Does 3 times 1.6, that would be 4.8. And 4 times 2.3, that would be 9.2. That does add up to 14, so that works. And this one must work also because I did the equation right there. I guess that is the answer. That one would have been a hard one to figure out by graphing, that's for sure. Let's try this one. I think it looks much easier. In this one, the y is already by itself, so I can skip that step, right? And I can go right to step 2 here, which is substitute what that variable equals into the other equation. So I take what y equals and I put it into the other equation in place of the y. And I get x plus, instead of x plus y, now it's x plus 3x. I think this is why we did that stupid basketball player problem, to learn how to substitute one thing for another. Woo! All right. And then I can go ahead. This is an easy one to solve, right? 4x equals negative 32. And I would divide both sides by 4 and get x equals negative 8. I now have half of my answer. And I would get the other half by substituting that back into the first equation. Y would equal, instead of 3 times x, 3 times negative 8. So y would equal negative 24. We have just solved 2 of these by the substitution method. I hope you followed that. Let me show you a couple more things. First of all, this is an example of a problem that you might have done last night for homework. It's one that is actually, in my opinion, a special case where both equations have the y by itself. And our book calls this the equal values method. But to me, what you're really doing is you're still just doing the substitution method. We're going to take what y equals over here and put it in for y over there. So instead of y equals, we'll have 2x plus 7 equals x minus 1. It's really just the substitution method, but our book calls it the equal values method because these two values are equal to each other because they're both equal to y. I don't feel like we need to finish solving that. I just wanted to point out the equal values method again. Let's go to the back. I got a couple things and we're done. Okay, it is possible for a system to have no solution. No solution means that there would be no ordered pairs that could make the equations true at the same time. It is also possible for there to be infinitely many solutions. That means there would be infinitely many ordered pairs that make both equations true. And I have a couple examples down here, I think, to show you probably. Here's how you know if there is infinitely many solutions. When you go to do the substitution method, you are left with all numbers. Both variables cancel out, and you're left with a true statement. In math, a true statement is called an identity. You are left with an identity like 2 equals 2 or 0 equals 0. Whereas if you go to use the substitution method and you solve the system and you get a false statement like 8 equals 2, then you know that that system has no ordered pairs that make it true. So let's go ahead and see what would happen here. In this first example, I am taking what x equals and I am substituting it in for x. So that's going to give me 3.5. Instead of 3.5 times x, it's going to be 3.5 times negative 2y plus 4 plus 7y equals 14. And I would go ahead and solve this by distributing the 3.5, right? Everybody understand how I made the substitution first, though, right? So then I'm going to distribute the 3.5. 3.5 times negative 2 is negative 7y. 3.5 times 4 is, let's see, it'd be 14. It would be positive 14. So I get that. And then look what happens when I combine my like terms. I have a positive 7y and a negative 7y. So they are going to cancel each other out, leaving me with 14 equals 14. This problem, let's see, the variables canceled out, but I was left with a true statement, which means this one has infinite solutions. Now, notice it's not all solutions. There are infinite solutions, but not every ordered pair is a solution. So it's not like a single equation where it might be all real numbers. It is just there's infinitely many ordered pairs that work. But not all ordered pairs work. All right, then I have this second example over here. Let's go ahead and do it. It is already set. I have the y by itself. So I can go ahead and substitute that amount in for y in the other equation. And I would get, instead of y, I would get 3x minus 11 minus 3x equals negative 13. I have made the substitution. Then I go ahead and combine my like terms. My like terms are the 3x and the negative 3x, and they cancel each other out. Look at that. And I am left with negative 11 equals negative 13. This is an example of a problem where when I went to solve it, the variables canceled out, and I'm left with a false statement, which tells me this problem has no solutions. All right, one more thing and we're done. I think that you can look closely, well, a lot of times I wrote this. A lot of times. This is not a totally necessary skill, but it will make it faster for you. If you look closely, a lot of times you can tell in advance if there will be one solution, right? One solution, or no solutions, or infinitely many solutions, by looking at the coefficients and the constant terms. Here's how you know. It's a little confusing, but I think you'll get it. There are no solutions if the variable terms are multiples, but the constants are not. There are infinitely many solutions if the whole equation is a multiple of the other one. And if neither of these things happens, then there's one solution. So let me show you what I mean by that. Let's look at this first equation. And it looks like in this first equation, look at the x's. See how the x got multiplied by negative 3? You know, this one is negative 3 times this one. And that's also true for the y. Negative 3 times 7 is negative 21. And that's also true for the negative 4. Negative 4 times negative 3 is 12. The entire equation is a multiple of the first one. Everything in the first one got multiplied by negative 3, right? Negative 3 times x, negative 3x. Negative 3 times 7, negative 21. And negative 3 times 4 is 12. So if the entire equation is a multiple, this one has infinite solutions. And I don't even have to solve it. Whereas the second one here, it looks like the 6x could be multiplied by 2. The y could be multiplied by 2. But the 10, sadly, the 10 is not multiplied by 2. So when the variables are both multiples, but the constant term is not, that's the first one. That tells you this has no solution if I went to solve it. We'll talk more about these things as the chapter goes on. Just give you a little heads up there, I guess. And that's the end of the notes. Good luck on your homework.